Okay, these are homework from last week. These have to do with work and its connection to kinetic energy. So I'm just going to go through them real quick. Okay. So the first question asks, in which of the following situations is zero net work done? Okay, so we've got a ball rolling down an incline plane, a projectile falling towards Earth, a student stretching a spring, and a box pulled across a rough floor at a constant velocity. Okay, so remember, work is our net external force multiplied by our displacement, where those are parallel to each other. Okay, you have to have a net external force to have work. And remember, a long time ago, we talked about how our net external force equals mass times acceleration. So you got to have acceleration to have a net external force. So of these situations, these are some clue words right here to help us know that D is the one where zero net work is done because the box is pulled at a constant velocity. That means there's no acceleration. That means this is zero. So that means this is zero. And that means that this is zero because there's no net external force. There's forces from friction, but they're being offset by whatever the applied force is that the box is pulled at to keep it at a constant velocity. Any of these items are accelerating. If this is rolling down a plane, it's accelerating. We know this is in free fall. It's got acceleration due to gravity. Stretching a spring requires a net external force that's going to accelerate that, basically change the velocity of the spring, right, from zero to whatever as it's stretched. So all of those have an acceleration. That means they all have a net external force value. Okay, worker pushes a lawnmower with the handle at an angle of 60 degrees to the horizontal. So here's somebody who's working on his lawn, and he's got, not very good at drawing a lawnmower, but he's pushing on the handle, and it's at an angle of 60 degrees. And he's applying a constant 20 Newton force and moves it a distance of 100 meters. We want to know what work was done. So here we can use our net force times our displacement. And then here we've got to take the angle into account because they tell us that he's pushing it at an angle of 60 degrees to the horizontal. So remember, that's your angle between your force and your displacement. Okay, if they're not parallel to each other, then we've got to pick up the piece that is parallel, which is cosine. Remember, cosine is going to be adjacent over hypotenuse. So that gives us this piece that's parallel to the displacement because he's moving this along this way as he's mowing the lawn. So this is my displacement, and then that gives me the parallel force piece. So I just multiply 20 newtons for the force by 100 meters for the displacement by the cosine of 60, and I got 1,000 joules when I did that because cosine of 60 is actually 0.5. So, okay. All right, a student is wearing frictionless inline skates on a horizontal surface, and a friend is pushing them with a constant force of 45 newtons. How far must the student be pushed starting from rest so her final kinetic energy is 352 joules? Okay, so this is where we can use work equals a change in kinetic energy. Okay. And in this case, we're going to solve for the displacement. Okay, how far must the student be pushed? That tells me I need a length. So I've got force times displacement equals my change in kinetic energy. And my change in kinetic energy is this 352 joules because she starts from rest. And then we want to know what her final kinetic, well, we want to know how far she's got to be pushed to get to a final kinetic energy of 352. So I can set net force times displacement equal to that change in kinetic energy, which is the 352 joules here. I know my force is 45. I'm solving for my displacement. I'm given the final kinetic energy, and then I solve for D, so I'm just dividing both sides by 45. This is the same like as 1/2 mv final squared minus 1/2 mv initial squared. We're just given this in terms of the whole kinetic energy, so we don't have to worry about mass or velocity. And we also know that this term is 0 because she is starting from rest. So her initial velocity is 0. Okay, just so that's clear. Okay, so anyway, I divided both sides by 45 and I got 7.8 meters. Okay, a 2,100 kilogram car starts from rest at the top of a driveway. So it starts up here. The driveway is sloped to the 20-degree angle. There's a frictional force as it slides down the driveway. Okay. So by the time it gets to the bottom of the driveway, it has a speed of 13.8 meters per second. We want to know what the length of the driveway is. So again, we are solving for displacement. This one's a little trickier because it's on an incline, and we need to find the net force on the car. So we got to go back to some dynamics here. Which I'm sure we remember all of this. Okay, so things we know the mass of the car. We know the force of friction. So remember when you're on an incline, okay, you've got your normal force perpendicular to the incline. Gravity points straight down, so that means we look at gravity as components. And then friction is always pulling in the opposite direction of motion. So if my car is moving down the driveway this way, my friction's pulling back. And then I've got an X component of gravity that's really what's responsible for the acceleration. Okay, is this piece right here. My net force is going to be this piece minus the friction. And this was the incline plane that we looked at a long time ago. Okay. Let's see, what else do we know? We know our final velocity is 13.8. We know we started at rest because it says starts from rest. So we can use work equals a change in kinetic energy to solve for this displacement. Before we use this, we've got to get our net force. So that's going to be this X piece of force of gravity minus force of friction. Okay. And going back to the X piece, it's going to be M times G times the sine of that angle. And I won't go back through all that, but that's how we solved for this. Okay. And then we got to take the friction off of that. They give us the frictional force of 4,000 newtons. So when I multiply this all out by the sine of 20 minus 4,000, I got 3,039 newtons. And then I'm going to put that in here for net force. My change in kinetic energy, my initial velocity was 0. Okay, so I'm really just doing 1/2 times m times velocity squared, my final velocity. And I divide all that by the force. And I ended up getting 66 meters as the length of the driveway. Okay, so let me continue in the next video.